Yes, this is happening. Okay, so would anyone please tell Oishwarya to again join?
Yes, ma'am, I've said her.
Okay, okay, okay. Okay, so we introduced basically the things, and I think you got some time to check the slides, and you also checked the book, So in the beginning, you can start with Stock and Watson, and later we can have a mix and match with several other things. Okay, so just to recap several things, I'm starting from this point. So we have one exact functional form. This exact functional form sometimes is called the population regression line. Exact functional form means, what theoretically we are framing or what we have in our mind. The relation between price and demand, the relation between rate of interest and investment, the relation between consumption and income. So the idea we have from theory or historically we have some ideas. So exact functional form can be considered as the population regression line, something which we are expecting for the entire population. Okay, so this is the ideal thing, the population thing. Okay, so exact functional form or the population regression line, which is our starting point, is given by y is equal to alpha plus beta x. Last day I mentioned, while we are beginning with this entire thing, we are keeping the entire concept very simple, and for that matter we are considering only one explanatory variable. Okay, by this time you understand y is the explained or the study variable, x is the explanatory variable, regressor of the model. Okay, so x is the explanatory variable. So to begin with, to keep the things simple, we are considering a single explanatory variable x. However, in reality, actually, a number of explanatory variables work to explain the variation in y. From your micro theory, if you consider the simple demand curve, in that case, not only price of the commodity affects the demand, rather price of the substitutes, price of the complementary commodities, income, taste preference, age, gender, advertisement. There are many things, which affect the demand for a particular commodity. Okay. So again, savings decision not only depends on rate of interest, it also depends on a number of issues. So if you look at the reality, actually to explain the variation of the study variable, you need a bunch of explanatory variable. And it may happen once you consider a bunch of explanatory variables, still there are few, which may have some impact on y. Okay, so it's a big thing. However, to keep the matter very simple, we are starting with a single explanatory variable x. So our exact functional form or the population regression line to begin with is given by y is equal to alpha plus beta x. Alpha is the intercept, beta is the gradient of this model. Beta is capturing the effect dy dx, how y changes for 1 unit change in x. Okay, so this is the population thing, exact thing. Now we are going to the reality, and you have some idea, how we consider the sample, what are the different methods of sampling, and you read a number of things regarding at least about random sampling. Okay, so you have some idea about the sampling methodology, and purposive sampling, I hope, the random sampling, stratified sampling, etc. So we are collecting observations, and we are trying to collect a set of representative observations. Okay, so now I have the quantity demanded for first individual, second individual, third individual, etc. That is For an individual, I have observations on demand. Similarly, I have observations on prices too. Okay. So for this particular price, what this particular individual is purchasing. Or you can consider for this particular price, what a particular household is purchasing. Or it may be a country-wise data or state-wise data, whatever. For the price of orange in these states, what will be the state purchase of oranges. So that can be the thing. So I'm putting one I here. I am not writing y, rather I am writing yi. Yi is equal to alpha plus beta xi. So I'm bringing I, observations, where I is equal to 1, 2 to n. Okay. So this is the thing. Not only this, there is one more change in my equation, and that one more change is incorporation of a random error component ui. Random error component ui. So last day I mentioned, while we collect a bunch of observations, and if I have a fixed line in my mind, all the observations will not lie on the line. Some of the observation will lie above the line, on the line, below the line. Okay, so everywhere there will be points. So you will get a scatter. That scatter is following a pattern, and therefore, the kind of fit you are trying to have, that may be the right fit. Okay, so while you are considering or while you have some idea that the relation between y and x will be negative, the scatter may be like that, it may result in a negative plot. However, when you consider the scatters or the observations, it is likely that some of the observations will lie on the feet, some above the feet, below the feet, etc. Okay. So there will be a gap between the observation and the feet you have in your mind. Okay. So these gaps are called errors. And last day, I sent you the slides, and I hope you checked the matters. And I think you have some idea about what may be different sources of these errors. I had a slide on this. Yeah, this one. Did you check this one? Everyone? Nobody checked.
Ma'am, you said you are going to come back to three slides after you discuss about regression and something like that.
Okay, and in mail I told you to check this. Okay, so no problem. So there are several sources why an error or disturbance exists. Okay. One thing I mentioned, that is the graphical thing. When we consider the scatters, all the points will not lie, etc. Now, why this thing will happen, or why the concept of error is emerging, why the scatters do not lie on the feet, why there will be some scatters above the line, why there will be some scatters below the line, etc. Okay. So there are different sources. Number one, omission of explanatory variables. Omission of explanatory variables. Now, I told you to begin with, I'm considering a very simple model. I'm considering demand depends only on price. Now, if I consider demand depends only on price, there are several other aspects which I'm not considering. So, when you are collecting demand for each and every individuals, it is not only price determined. So, it is, for some people, it is heavily determined by taste and preference. For some people, it is mainly gender determined. For some people, depending on the nature of advertisement, for some people, it depends on what is the price of the related commodities. For some, income matters most. Okay, so only maybe for few people, really price matters most. Okay, so there are these things. Since you are not considering a number of explanatory variables which may heavily affect the demand for the concerned commodity, that this omission of the explanatory variables creating a distance between the scatter and the line, okay, or generating the error. Now, if you think that I'll consider at least 10, 12 explanatory variables, then also in reality, there will be again another set of 10, 12 variables which may affect the variability in the demand for a concerned commodity. Okay, so this is an unending process. There are number of variables. Just a minute. Hello. Sorry. So, there are so many factors in reality which may affect the variation in the study variable. In one single study, it is difficult to accommodate all this. So if you accommodate 12, there are another 12. If you accommodate 24, there may be another 6. So all these things are there, and for that matter, there will be a presence of a distance between a scatter and the fit. The second possibility is aggregation of few variables in a single variable. Sometimes what we do, instead of considering a number of variables, we consider an index framed by a few variables, or we use a concept, which carries the essence of number of variables. For example, suppose you consider demand will be determined by quality of the product. Demand will be determined by the quality of the product. Now, the term quality varies from person to person. Okay, there are few people who think that if the color is pink, then the quality is good. And there are people who really assess the content and then tells that if the content is like this, then it will carry this kind of quality, or this will indicate this kind of quality. Okay, so the concept of quality, that itself varies from person to person, household to household, gender to gender. So if you consider this kind of variable which captures, last day I talked about happiness. Happiness, is created by interaction of number of variables. So if you consider this kind of variables, which itself is aggregation of few variables, in that case, what are the variables actually it is carrying? What will be the absorption capacity of these variables? All these things will matter, and you are understanding that it is very difficult to have a perfect concept which carries really a number of things. So aggregation of few variables is another problem. there may be some issue related to model misspecification. Now, what is misspecification? Yi may not be affected by xi, but by xi minus 1. So, you have some concept about the differential equation framework. For simplicity, if I consider time to be discrete, and if you consider a Cobb-Douglas type framework, you know that in that case, supply in the tth period does not depend on price of the tth period, rather it depends on price of the t minus 1th period. Suppose now you are considering the agricultural market and you are trying to estimate the supply equation. However, you are not considering this kind of lagged framework, rather you are considering the instantaneous adjustment. However, the real model is the lagged model. Again, the lagged may not be the first 1 period lag, there may be the 2 periods lag which is relevant, 5 periods lag which is relevant, etc. However, you are considering, suppose, the instantaneous adjustment. So if you consider the instantaneous adjustment, however, the true things or inherent things are 5 period lagged adjustment, in that case your model is misspecified, and for this misspecification, errors will come up. Another possibility is functional misspecification. We are considering a linear framework. However, it may happen that xi is not working, rather xi square is working, or say xi to the power 5 is a good choice. Okay. So there may be some functional misspecification too, or you are considering a linear framework. However, it should be a non-linear framework. Non-linear framework will be the better description of the relationship between yi and xi. Okay, so there is a chance that your function is misspecified, and then also there will be the possibility of occurrence of errors. Finally, you may face the problem of measurement errors whenever you are going for any kind of sampling exercises. Measurement of one or several variables may be incorrect. Whenever you are going for the sampling exercise, you have some idea that though we try to find out the representative sample, frame the sample following a number of proper methodologies, then also there may be some problem regarding collection part, there may be problem regarding the presentation part, so there is a possibility that there will be some sampling errors or measurement errors. Okay, so mainly these are the sources, these are the 5 main sources which may generate error in the entire analysis. Okay, and for that matter, while we present something which is based on the observations, we present the model as yi is equal to alpha plus beta xi plus ui, where ui is the random error component. Now, if we consider expectation of yi is equal to alpha plus beta xi. So, this equation can be also rewritten as expectation of yi plus ui. Actually, expectation of yi is the population thing. On the basis of the sample, we can expect the value we have in our population. So expectation of yi, which is alpha plus beta xi, is nothing but the population part. So the sample based regression model can be presented as population regression plus the error component. Okay, or expected value of the sample regression, that is expected value of yi plus ui. Expectation of yi means expectation of the sample counterpart, and the total expectation of yi, this term indicates the population counterpart. Okay, so just I am writing the thing. If you just consider this one, this means expected value of the sample observations. And if you consider this entire thing, this means you are considering the population counterpart. Okay, so expected value of the sample counterpart is equal to the population counterpart. Okay, so yi is equal to the population counterpart, which we have in our mind, which we learned from our theory, plus the error component. Okay, now our objective will be to estimate the demand equation, or estimate the supply equation, or estimate the savings or investment equation or consumption function, etc., after collecting the data. That means I want to find out why I had estimated demand. Theoretically, I learned all these things. Now I have the database with me. So on the basis of the database, I want to find out the estimated demand, estimated supply, estimated consumption function, investment function, etc. Okay. So on the basis of this empirical exercise, our final objective is to calculate yi hat, estimated value. Now, estimated value is given by alpha hat plus beta hat xi. So the entire objective of this exercise is to find out the optimum values of alpha and beta given by alpha hat and beta hat. We have to find out the values of alpha hat and beta hat. Now, given this information, how we can derive this alpha hat and beta hat? We are finding that the difference between the theory and the practical exercise is the random error component. So if I can minimize this random error component, we will be able to derive an optimum fit. If I can minimize these error probabilities, that is somehow I can minimize the UI part. In that case, what I'll estimate from my sample observations, that will be very, very close to the population counterpart. Okay. So the objective will be to minimize the error part and thereby estimate the two unknown parameters, alpha hat, unknown parameters, alpha and beta in this model. And finally find out or finally present the estimated model yi hat, which is equal to alpha hat plus beta hat xi. Now, before giving or getting some idea about how to minimize the error, how we really estimate the unknown parameters of the model, we need to understand the nature of the error term. In the last class, I started to discuss some assumptions based on error. Okay? And all these assumptions or the nature of the error will tell us what kind of model it is and what will be the proper estimation technique for this kind of model. As I mentioned, we are trying to frame a classical linear regression model, CLRM framework, classical regression framework, classical linear regression model framework. Okay, so the assumptions we are making, these assumptions are related to the classical model, or these assumptions will make the model a classical one. Last day I discussed two assumptions. The first two assumptions I could complete. One, expectation of UI is equal to 0. Okay, this assumption, error is unbiased and expectation of UI is equal to 0. I mentioned that this is the consistency requirement of the model. In example sense, we cannot start with a non-zero error. If I start with a non-zero error, I explained this I can capture in my intercept term. So in example sense, mathematically, we should not start with some non-zero error. And if I consider the statistical sense, I mentioned that if error is really random, some of the scatters will lie above the fit, some of the scatters will lie below the fit, and if observations are random, in that case, positive and negative discrepancies, in other words, the positive and negative distances of the scatters from the fit will interact with each other, and finally they will average out. That means expected value of the error, expectation of UI is equal to 0. And the second assumption I mentioned, that is variance of UI this is a constant. Variance of UI is a constant, and that is given by sigma u square or sigma square. This assumption is called homoscedasticity assumption. This is not at all a consistency requirement. This is a stringent assumption. We are assuming that for each and every groups for whom we are collecting the data, there will be no variability in terms of the relationship between Y and X. Their variance or the dispersion of the interrelation between Y and X, that remains constant across the groups. As an example, I mentioned that if I consider the relationship between consumption and income at macro level, in that case, the gradient indicates MPC, marginal propensity to consume. Now, while I'm collecting the income and consumption data, in that case, people are coming from different income level. However, for different income levels, I'm not considering the MPC will vary. Theoretically, I have the knowledge for the lower income group, MPC will be very high and almost close to 1. And for the higher income group, MPC will be very low and almost close to 0. However, homoscedasticity assumption indicates that there is no variation across different income levels or different income groups. This variance is constant. It is not sigma I square. It is not varying from group to group. There is a constant dispersion for all the groups. So these are the two assumptions which I explained in the last class. And I have to develop few more. Any question?
Ma'am.
Yes. Yes, okay.
ম্যাম ওখানে আপনি পপুলেশন রিগ্রেশন লাইন লিখেছেন, ম্যাম ওটা এক্সপেকটেশন অফ y হবে না?
Expectation of y is there. I have written expectation of y only.
মানে ফার্স্ট লাইনে মানে
alpha plus beta xi plus ui, and after that I have written expectation of yi.
ম্যাম ফার্স্ট লাইনে যেটা আছে ওটা তো মানে পপুলেশন রিগ্রেশন লাইন।
Bring observations in the first line. I didn't bring observations in the first line. I am just presenting the theoretical framework. Okay, exact functional form. The population line indicates the exact functional form. There is no observation. Okay, so there is no question of considering expectation. When I am collecting the observations, that is when I am talking about the sample observations, I have yi in my hand. In that case, expected value of the sample observations will be exactly equal to y, that is alpha plus beta x. Okay, got the idea, Abhishek?
Yes, ma'am. আর ম্যাম যখন এক্সপেকটেশন অফ ওয়াই আই লিখছি ম্যাম ওখানে গিভেন এক্স আই হবে কি?
Yeah, this, please, take some time. I'll tell all these things again later. Okay.
ওকে ম্যাম.
A conditional thing I didn't bring, Let me again talk about the assumptions and then introduce the that thing. Okay.
ওকে ম্যাম.
Okay, so let's come back to the assumption part. So I completed up to uniform variance and I told you about these graphs, So now I am at third assumption. I'm considering the covariance between Ui and Uj. Covariance between Ui and Uj. Okay. That is a relation between two errors, Ui and Uj. Both I and j are running from 1 to n. However, I not equal to j. Both I and j are running from 1 to n. However, I not equal to j. This concept. So covariance formula can be written as expectation of ui minus expectation of ui into uj minus expectation of uj. Okay, now both expectation of ui and expectation of uj, these two things are equal to 0 by the assumption of, by the first assumption, by the assumption of unbiasedness of the error term. By the assumption of the unbiasedness of the error term, expectation of ui is equal to expectation of uj is equal to 0. So simply I can write this entire expression as expectation of ui uj, expectation of ui uj. Okay. We assume that this expectation of ui uj is equal to 0. This expectation of ui uj is equal to 0. We assume this relation between ui and uj, covariance between ui and uj is equal to 0. That is, the two errors are independent. Ui and uj are not related. They are independent to each other. We are assuming this. This assumption is called disturbances are pairwise uncorrelated. Disturbances are pairwise uncorrelated, which is known as assumption of non-autocorrelation. Assumption of non-autocorrelation. Okay, so I'm assuming there is no correlation between the two error terms. So it is no correlation assumption. Now, why the term auto is there? In general, when we consider the concept of correlation among the variables, we consider the correlation between x1, x2, x3, x4, etc., where x1, x2, x3, x4 are totally different variables, or correlation between, say, xy, z, xy, yz, etc. So in that case, all these x1, x2, x3, etc., or xy, or xz, or yz, these variables are totally different variables. Here, we are not doing that. We are considering the same term, the same error. Both I and j are running from 1 to n. However, at a particular point, I is not equal to j, because if I is equal to j, in that case, you are getting the variance part. Okay, you will get actually expectation of ui minus expectation of ui whole square then, if I is equal to j. and you will get the variance part. So to maintain the definition of covariance, you are considering the same error. However, uh, you are considering two different observations. That's all. You are considering two different observations of the same error. Since you are considering two different observations of the same error, not two errors, two different observations of the same error, therefore it is called autocorrelation. It is called autocorrelation. So the assumption is called non-autocorrelation. Okay. Now what it is implying, or theoretically how we will understand the idea of non-autocorrelation. Okay. Now to understand the idea of non-autocorrelation, always it is better to consider an example which is based on time. Okay. Suppose I'm considering industry X. Okay, IT industry, say any industry X. Okay, and then I'm considering output okay, and then same industry however two periods. Okay, and suppose I'm considering a Cobb-Douglas type function, or forget about Cobb-Douglas type function. I'm considering that the output, sorry, this kind of framework. Okay, output of the X industry depends on capital we are investing on industry X. Okay, so alpha plus beta kx. Now if I like to estimate these production equation for the period 1995 to 2005, and then for the period 2006 to 2015. Okay, in that case I'll consider the observations for different periods. So just I'm putting I here, and this one I am considering. Okay, this kind of framework I am considering. Okay, now UI, when I am considering the first period, captures the essence of explanatory variables apart from capital, essence of all other explanatory variables apart from capital. In other words, now apart from capital, there are several variables which actually determines what will be the output in the X industry for this period. To keep the model simple, I have considered capital explicitly. However, there are, say, 15 very important factors which have important role to explain the output of the X industry. So, effect of all these 15 components are there in the error turn. Now, After estimating the first equation, when for the same industry, I am estimating the same model for the second period, 2006 to 2015, we will find that almost the 15 variables we understand which may have impact on output, all these 15 variables are working, or at least 12 of the 15 variables are still working. 12 of the 15 variables, and then say 10 new variables. These are affecting, apart from capital, these variables are also affecting the output. Okay. So there will be common 12 factors which are there in the error path for the period 1995 to 2005 and for the period 2006 to 2015. So there is a common subset of variables which are there in the error counterpart for both the regression models, and that may result in interrelation of the errors of the two regression models, because there is a subset of factors which is common in error terms of both the periods. Okay, and that results in a correlation between the two errors. In reality, whenever we go for any kind of time series analysis, we find this issue. We find this kind of problem. The errors are related to each other across different periods because you are considering the same industry or same country. And for the same country, same industry, if you can change the time zone only, there will be some common factors which are always working to establish the relationship between Y and X. And that creates noise in the system and makes the error component auto-correlated. However, to begin with, I am making an assumption that errors are not correlated to each other. They are independent to each other. In the last class, I talked about homoscedasticity. Then also you found that it is a stringent assumption. It is heavily restricted assumption. Actually, across the group, there is a possibility that the interrelationship between Y and X will vary. The dispersion of the relation will vary. However, we are considering the dispersion is constant. Just like that, today also we are assuming, though there is an immense chance that there may be some interrelation among the error terms, to begin with, we are assuming that there is no correlation between the two error terms. Okay? Or in other words, we are assuming that covariance between Ui and Uj equal to 0. Okay? Covariance between Ui and Uj is equal to 0. Got it? Any question?
Ma'am,
Yes.
so for example, the error of the observation of one time period, if we denote that by ui, and the error of the observations from another time period, there is no correlation between them. It is an
We are
assumption.
assuming, yeah,
So
we are
that
assuming
is
that there is no common factor, Aziz. There is no common factor between the two regression models. Aziz, only K determines output, and if there are several factors, those variables are totally different in period 1 and period 2. That we are assuming.
right.
These assumptions are a bit unrealistic. However, to begin with, always we will start with the the easiest, context, because we need to learn the basic things first, and there will be some point when we will actually consider the variance to be sigma I square. That is, we will handle the heteroscedasticity issue. Also, we will handle the autocorrelation issue. But to begin with, we are considering a very simple structure. We are assuming that there is no interrelation among two error terms. Okay, ui and uj are independent. Covariance between ui and uj is equal to 0. So next I'll go for the fourth assumption. Just this assumption is related to xi and ui. Okay. So I'm writing the regression model once again. Yi is equal to alpha plus beta xi plus ey. Okay. Now in the right hand side, I have two variables, xi, the explanatory variable, and the random variable ui, which we are calling the error term. So there are two variables in the right hand side, xi and ui. So these variables, the variables that will be there in the right hand side, they should not be related to each other. The assumption is, or the requirement is, the variables we have in the right hand side, they should not have any interrelation among themselves, because if they have interrelation among themselves, xi and ui are functionally related, in that case, you will be not able to frame a linear model. You will be not able to frame a linear model. If xi and ui again are functionally related, in that case, you are asking the basic concept of linearity. We want to frame a classical linear regression model, and for that matter, we are not allowing any functional relationship between the variables which we have in the right hand side. Therefore, we are assuming that covariance between xi and ui is equal to 0. Covariance between xi and ui is equal to 0. This we are assuming. Now, here you need to take notes. Okay, I hope all of you have pen and paper with you, and you need to take some notes here. So first of all, the assumption is covariance between xi and ui is equal to 0, because this is the requirement to maintain the linearity of the structure of the model. So this is the assumption part. Now, if I consider xi is a non-random variable, non-stochastic variable, then this assumption is trivially satisfied, because ui is always random. So if the nature of the two variables are totally different, in that case, their covariance will be definitely equal to 0. Okay. However, this is only a sufficient condition. That is, non-stochasticity of xi is a sufficient condition to ensure covariance between xi and ui is equal to 0. Xi may be random or stochastic, and if that random or stochastic variable is independent of ui, then also the assumption will be satisfied. Okay, so in general, in most of the books, or under most of the circumstances, you will find that we are considering xi to be non-random. Actually, we consider xi to be non-random to have the sufficient condition to generate the or to fulfill the assumption covariance xi ui is equal to 0. However, it is not a necessary requirement because xi may be random but still independent of ui. Okay, so please take note. First, you write down the assumption covariance xi ui is equal to 0. Then you add in the note, if xi is non-stochastic, within bracket non-random, if xi is non-stochastic within bracket non-random, this assumption is trivially satisfied, or this condition is trivially satisfied. Hence, non-stochasticity of xi is a sufficient condition to have covariance xi ui is equal to 0. Non-stochasticity of xi is a sufficient condition to have covariance xi ui is equal to 0. Next, however, non-stochasticity of xi is not the necessary requirement to have cov xi comma ui is equal to 0. Non-stochasticity of xi is not a necessary requirement to have covariance xi ui is equal to 0. Add xi may be random, however still independent of ui. Xi may be random but still independent of ui's. Anyone, any question? Anyone, any question up to this?
ম্যাম
Yes.
ম্যাম ইন্ডিপেন্ডেন্ট তো নাও হতে পারে।
In that case, you are not satisfying the assumption and that random xi will not work.
ম্যাম কোভেরিয়েন্স 0 মানে তো মানে আনকোরিলেটেড, মানে আনকোরিলেটেড হলে ইন্ডিপেন্ডেন্ট না মানে নাও হতে পারে।
I'm considering this as a general concept, So when we are considering the covariance, because we are considering the linear framework, we are not talking about any kind of non-linear relationship, okay? So since our framework is linear, if covariance xi ui is equal to 0, in that case xi and ui will be independent to each other. Okay.
Yes, ma'am. Okay.
Everything you have to consider only for the linear model because we are considering a linear construct. Okay, so Any other question? Anything else? Now look in the slide. There is one other point. Single equation linear model indicates there is no interaction among the independent variables. X's are independent among themselves, and the second point is X's are independent of U. Okay, I have generally written this slide, and for that matter, the first issue is coming. Here we are concentrating on a very simple framework where there is one explanatory variable only, xi. However, the model can be extended as yi is equal to beta naught plus beta 1 x1i plus beta 2 x2i plus beta 3 x3i and so on, beta k xki plus uy. This kind of framework for all I is equal to 1 to n. Okay, so it is a k variable framework. Okay, instead of a single explanatory variables, I have a number of explanatory variables, k number of explanatory variables. So x1, x2, x3, x4, it is up to xk. Okay, k number of explanatory variables. So the assumption is telling that there will be no interaction among the independent variables too. Okay, as I mentioned, to maintain the linearity, etc., we need that there should not be any functional relationship between the variables we have in the right-hand side. So, if I have a number of explanatory variables in the right-hand side, there should not be any correlation among these variables too. Later, we will handle this issue when we will consider a multiple regression framework or multiple explanatory variables. If there is correlation among x1, x2, x3 up to xk, or correlation among the explanatory variables, that problem is known as this problem is known as multi-collinearity. If there is correlation among the variables x1, x2, x3 up to xk, this is known as the problem of multi-collinearity. Okay, and in presence of multi-collinearity, there will be several issues. You will be not able to estimate the model, etc. So if there is multi-collinearity, first you need to remove or tackle the multi-collinearity, and then only you will be able to estimate the parameters of the model. Okay, so always there will be some issues if there is some interrelation among the variables you are considering in the right hand side. And for that matter, I have mentioned single equation linear model needs that there should not be any correlation among x's, and there should not be any correlation between x and u. Okay, so later I'll mention about when I'll introduce the multiple regression model, if I have any time to do so, then I'll talk about the multicollinearity issue too. However, for the time being, you remember that there should not be any correlation among the variables to the right hand side. Though the basic assumption here we are making regarding the error term u, and that mainly focuses on the issue that there should not be any correlation among x and u. So at this time point, I have no focus on the multicollinearity thing because we are discussing only a two variable case. We have a dependent variable and we have an independent variable. So we do not have more than one explanatory variable at this moment. So this multicollinearity issue is not our objective to address, or we should not concentrate on this. Just I mentioned about this thing, there are this kind of issues that I want to mention here. That's all. The main thing is, the main assumption here on which we should focus, that is covariance between the error and the explanatory variable should be equal to 0. And here non-randomness of x is a sufficient condition to satisfy this assumption. However, non-randomness of xi is not at all a necessary condition to satisfy necessary requirement, because xi may be random but still independent of ui. Okay, so next assumption is normality of the error term. Now I am giving an assumption which is based on the distribution of the error term. Distribution of the error term. Okay, so far I didn't mention anything about the distribution of the error term. So again, let's mention about the 4 assumptions. Already we did. Expectation of ui is equal to 0, unbiasedness assumption. Number 2, variance of ui is equal to sigma square, a constant homoscedasticity assumption. Third, covariance between ui and uj is equal to 0, non-autocorrelation assumption. Fourth, covariance between ui and xi, that is covariance between the error and the explanatory variable, that should be also equal to 0. So these are the 4 assumptions already completed, and I didn't bring any distributional aspect there. Coming to the 5th assumption, I'm bringing the issue of distribution, how the scatters will be distributed around the fit. So look at the diagram as a 3D diagram, okay, 3-dimensional diagram, okay. So we have these x-axis and we have this y-axis, and this corner is actually making the diagram 3-dimensional. This fy is making the diagram 3-dimensional, okay. So as if the scatters are there around the line, Now when I'm considering the scatters around the line, the way the scatters are there around the line is generating a normal fit, a normal curve, okay. So scatters are normally distributed around the line, normal distribution of the scatter, okay. So the assumption is written as u just this is assumption number 5. Independently and identically distributed. Independently and identically distributed normally with, now what is expectation of ui? What is expectation of ui?
0.
And what is variance of ui?
Sigma u square.
What is the variance?
Sigma u square.
So ui is distributed independently and identically normally with expectation of ui is equal to 0 and variance sigma u square. Okay, so the scatters are distributed normally around the fit. This is the assumption. Take a note. Note. While we estimate a regression model using the ordinary least square technique, using the ordinary least square technique, OLS, ordinary least square technique. We do not need the fifth assumption. We do not need the fifth assumption of normality. In other words, estimation part does not need the distributional aspect. Estimation part does not need the distributional aspect of the error term. This distributional aspect will be used. In context of hypothesis testing part. Okay. So up to estimation, especially if you use the ordinary least square technique, you do not need the fifth assumption. Your entire exercise will be based on first 4 assumptions. Only coming to the hypothesis testing part, you need the assumption of normality. Coming to the hypothesis testing part, you need the assumption of normality. Okay, so again, these are the 5 assumptions which are the core assumptions of the regression model. Okay, these are the assumptions which make the model a classical model. These are the assumptions which make the model the classical model. Okay, classical model. Okay, so please take note on that fact too. Assumptions 1 to 5 make a model a classical model. Make a model a classical model. And generates a CLRM. Classical linear regression model.
मैम CLR में assumption 5 टा लगे?
Yes.
Okay, ma'am.
For the estimation purpose, we don't need it. However, for the hypothesis part, very much, this assumption is very much required. So, all these 5 assumptions, starting from expectation of UI is equal to 0 up to the normality of the error term assumption, creates a classical framework, makes CLRM, classical linear regression model. Next, I'll tell about some assumption, which is general requirement. Okay, general requirement. This is not the assumption related to the random error component. Okay, this is the general requirement. And in this context, the idea of expectation, etc., I'll clarify. This is the assumption of no outlier. This is the assumption of no outlier. Okay. Now, while we are collecting the sample observations, there may be, look at this example. Okay, look at this example. Now, most of the observations are here. Most of the observations are here. However, there is one observation. There is one observation. Okay. And if the observation is like this, there are one or two observations like this. These observations are called the outliers. These observations are called the outliers. Okay. This is not belonging to the group. Now, in a classical linear regression framework, we assume that there is no outliers. Actually, if there is outlier, we need to remove this. Now, the question is why? Now, the regression framework we consider, these are the mean-centric approach. Actually, we try to calculate the expected value of y given x. This kind of concept. Expected value of y given x. So these are mean-centric approach. Okay. And for that matter, if the outlier is there, entire estimated model will be the erroneous structure. It will be a wrong calculation. Now, look at this structure. If you, do not consider the outlier, in that case, it is a negatively sloped line. However, this value is too far from all these, and pulling the entire line. So if this observation you include, in that case, the line will be a positively sloped line. Okay. So the entire set of observations are telling you there is a negative trend, negative relation between y and x. However, just for this single outlier, the entire equation will be a wrong equation, or entire estimated fit will be a wrong fit. Okay. To ensure that there is no large outlier, we assume that x and y have non-zero finite fourth moment. Okay, non-zero finite fourth moment. Or we are trying to put a restriction with respect to the kurtosis of x and y. Another way to ensure this condition is to assume that x and y have finite kurtosis. In other words, expectation of xi to the power 4 or expectation of yi to the power 4, all these values will lie in between 0 and infinity. All this expected value will lie in between 0 and infinity. Okay, so strictly less than infinity. It should have finite kurtosis. These two things are equivalent. If there is finite fourth moment, then only you will be able to have finite kurtosis. Okay. So outlier, you have to remove outlier, you have to handle, and why this will. Let me first tell these things and then I'll take question.
Could you just go back to the last slide?
Yes. Regression analysis is concentrated with the conditional mean modeling approach. We call this approach CMM, conditional mean modeling approach. Here, we are trying to find out, on the basis of the sample, we are trying to find out something which is very close to the population. So we have in our mind alpha plus beta x, this kind of thing in our mind. Okay. And on the basis of the sample observations, we are trying to do so. In other words, we are trying to find out expected value of y given the set of explanatory variables and the random error component. So we are trying to find out the expected value of yi, okay? And that will give us alpha plus beta xi, and this alpha plus beta xi will be very close to that of the population line, and for that matter we will be able to tell, you know, whatever we estimated from the sample, it is truly presenting the population, or this is truly presenting the theory. Okay, so this kind of approach is called the conditional mean modeling. Mean modeling, expectation of yi conditional, because you are calculating the value of yi given a particular set of observations on xi and naturally given a particular set of random error. One is more interested in studying the properties of the average and the nature of deviation from this average to come up with a general conclusion. Okay, so here our objective is to find out something average which will represent the theory. Okay, and if really we find for these set of commodities this particular thing is not holding, in that case we are calling it, these are the special cases, these are the deviations from the average, just like Giffen goods, you know. In general or conventionally, demand curve is negatively sloped. However, empirically, when we are investigating all these things, for these kind of necessary commodities, it may happen that the demand is positively sloped. Okay, so this is the idea. So conventional part which we have, and if really something we get which is not matching with the convention, in that case we consider this as the deviation, as the special cases. Okay, so here our approach is like that. So one is more interested in studying the properties of the average and the nature of deviation from this average to come up with a general conclusion. It is believed that, number one, if the sample is drawn objectively, and number two, if the relevant probability distribution is normal, that is symmetric around the mean with thin tails, then generalization would be possible. So we are keeping this point in our mind that if my sampling part is good, representative sample, objectively drawn sample I have, and then if I have the scatters which are normally distributed around the mean, in that case, you know, whatever result we will get, on the basis of that result, we will be able to reach at a general conclusion. Therefore, two major concerns of economists are random sample and normal distribution. The classical linear regression model presumes both, and the results are derived accordingly. If by any chance any one of these two specifications are getting questioned, the economists will try their best to protect their original position through suitable intervention. That is, if there are some observations which are disturbing, you know, you are not getting the normal fit, we will run the Jarber test, we will check the normality, we will adjust the position. So we will do a lot of things. However, generally, we will not try to come out of random sample concept and normal distribution concept, okay? Because the whole theory, etc., we learned on the basis of the database, we try to move around those theory, okay? So this is this type of econometrics we are doing in this class. However, don't think that econometrics is limited to only this kind of ideas, okay? We are starting with this kind of context. because we are introducing the introductory econometrics and we are trying to do something which is the part of our economics course. However, the literature is very vast, and nowadays mostly we work with the non-parametric type of concept where there is no hypothesis, no idea, no theory in the background. Always we consider the data as the starting point. Let the data tell us what will be the distribution. Let the data tell us what will be the hypothesis, okay? So that approach is the non-parametric approach. And all of you are very, very familiar with the name big data, okay? So all these things are really data related, and data actually reveals the result, and then we start analyzing the results. So these are the modern approaches. However, to introduce the subject, always the parametric approach or the idea we have developed so far as the part of a major course in economics, we have to start like this, okay? So therefore, we have started like this, okay? And later, when we will move for advanced courses, we will learn how we can come out of all these limitations, etc. Okay, so I'll stop here, if anyone has any question. So I have completed almost the entire assumption part, and I just have to explain the meaning of linearity that I'll be not able to do today, that I'll do in the next class. Any question on the new assumptions I made, or the idea about CMM?
Could you go back to the assumption of no outliers?
I didn't get you. Your voice is not clear.
Can you hear me now?
No, Ratrik, it's not clear.